In this game, two players take turns picking a number from either end of the array, and whatever they pick gets added to their own running score. Player 1 goes first, and both players play as possible to try to win. The narration should say that we need to figure out whether player 1 can end up with a score that's at least as high as player 2's. Eggman's level. Classic optimal. Play array game. Two players alternate taking from either end. Higher total wins. Return. Whether player 1 can force a win. You already know where this is going. This collapses to a single scalar recurrence instead of tracking two scores. That collapse is the entire problem. Everything else is bookkeeping. This is zero-sum, perfect information, alternating, move minimax, the same formalism behind Stone Game 2 and 3, just without the branching factor those add. Because it's zero-sum, you get to skip tracking both players' utilities entirely, which is the shortcut this whole video hinges on. Standard end picking, sum maximizing turn game. The one rule worth flagging for interviews, tie is resolved to player 1, so your terminal condition is defeat E0, not defeat E0, and off by symbol error that's easy to ship silently. Nums 1, 5, 2 both play optimally, answer is false. We'll use this array to falsify the greedy strategy in the next slide. Keep it in mind as the canonical counterexample. Interval dp over ig bears. The state space is every contiguous subarray, ONN of them. The real design choice is memodict versus dense 2D array. The dict avoids allocating unreachable ig, pairs, and skips tuple hash overhead entirely if you flatten to a 1D index, but the array wins on cache locality once you go bottom up, which is why the iterative version drops the dict altogether. Greedy fails because it optimizes your immediate gain while ignoring how it reshapes the opponent's next choice set. On 1, 5, 2, greedy grabs 2, hands the opponent a forced 5, you are left with 1, 3 to 5. There is no exchange argument that saves greedy here because taking an end changes which end becomes available next, so local optimality doesn't compose. Because the game is zero-sum on every turn, maximizing your score minus the opponent's is equivalent to maximizing your score under optimal opponent play. The opponent's best response is entirely captured by diffie or diffie JT1 in the recursion. This is the standard reduction for any two-player alternating additive payoff game. State space halves from score 1, score to a single relative value, and it generalizes directly to Stone Game ITI. The pair playing on the range starting at index I and ending at index J is worth the bigger of two options. Whichever player moves next takes nums at I minus the diff of the pair starting at I plus 1 and ending at J, or takes nums at J minus the diff of the pair starting at I and ending at J minus 1. The subtraction is doing the minimax work implicitly. Whoever moves next on the subrange is playing optimally to maximize their own diff, which from the current mover's view is a minimization, so it falls out as a negation rather than a separate min branch. The recursion tree is a DAG, not a tree. Diff 1002 is reachable from both diff 02 and diff 1003. Only undoubt distinct IJ states exist, but without memoization you rederive each one across an exponential number of paths, giving unmemoized runtime of 2000. Iterating by increasing length is just a topological sort of. The dependency DAG, the pair at row I, column J only depends on strictly shorter intervals, so length order guarantees every dependency is resolved before it's read. No recursion, no visited, state bookkeeping required. Direct transcription of the recurrence with top-down memoization. Worth noting, this recursion depth maxes out around n, so for large n you're one stack frame away from recursion error in Python, which is the actual reason to prefer the bottom-up version, not just style. Same recurrence, iterative, OA1, auxiliary stack. This is the version to write live. It also makes the space optimization obvious. Each length only reads from the previous length's row, so the full 2D table is more state than the algorithm actually needs. The Assembler solution. If you're asked to extend this to k-limited picks per turn or unequal turn order, this is the function you'd start modifying. The interval dp skeleton stays, only the transition changes. Player 1 loses the pair starting at 0, 1, that's 4 points. Player 2 loses the pair at 1, 2, 3 points. And for the pair at 0, 2, we take the bigger of 1 minus 3, or 2 minus 4, giving us negative 2. Negative diff, player 1 loses. Confirms the greedy counterexample from earlier wasn't a fluke. It's the actual optimal play result. Full table fills to the pair starting at 0, 3 equals 222, matching the actual optimal play score gap of 234 versus 12. Notice the magnitude swings hard between adjacent cells here. The pair starting at 1, 2 equals 228, Right next to the pair starting at 1, 3 equals negative 221, which is a good sanity check that you haven't mixed up. Nums to 2, 2, obvious Tyon scores, but is the return value true or false? This is the exact case interviewers use to check you actually encoded the tie rule instead of just eyeballing the recurrence. Diff row 0. Still true by the tie rule. If an interviewer pushes further, what if the problem instead defined a win as strictly outscoring the opponent? You'd change exactly one comparison operator. This is XC000. The rest of the DP is untouched, which is a good sign you've actually modeled the problem rather than pattern matched a template. Drop the memo and you get the raw minimax tree, branching factor 2, depth n, so 2 pi sin calls, over a million at n to 20, which is exactly LeetCode stated constraint ceiling for this problem, not a coincidence. It's a reasonable thing to write first live to establish correctness before optimizing. O(n) squared, time and space from the O(n) squared state count with O(n) transitions. The rolling array optimization is more subtle than usual here because the value at row I, column j reads the value at row I plus 1, column j, and the value at row I, column j minus 1. One from the row below, one from the same row. You can't do it with a single naive one. We pass in the wrong direction, you need to iterate I downward within each length. So the row I, column j minus 1 value is already I downward within each length. So the row I, column j minus 1 value is already the current get, length value at row I, column j minus 1. The zero sum reduction, max relative diff instead of two absolute scores is the transferable idea, not this specific recurrence. Stone Game 3 reuses it with a per turn choice of 1, 2 or 3 elements from the front only. Stone Game 2 adds a state variable for remaining move budget, M. Same reduction, bigger transition. If this was useful, hit like. Quick one. If the array has an even number of elements, does player 1 always win? Pause and think about it. Hints in the indices. Take a second. Yes. With even length, player 1 can force taking every even index or every odd index pile, so they always get at least a tie. Round 2. What does our DP recurrence give for a single element array? Guess before I say it. It's the base case of the whole recursion. It just means player 1 takes the only pile there is. That's exactly the base case in the table. The pair where the start and end are the same, that we start building from.